So, last time we went over the forward pass for a single layer perceptron, and now I would like to implement matrix multiplication into the forward pass. So if you don't know what matrix multiplication is, I will explain it now, and if you do, you can skip ahead using the timestamp that I hopefully remembered to put in the description. Okay. So before we can do matrix multiplication, we have to know what a matrix is, right? So a matrix is just a rectangular 2D array of numbers. Rectangular 2D array of numbers. Like this is a rectangular 2D array of numbers, right? There's 1 dimension, 2 dimension, and it can look at like any sort of assortment of these numbers, and it's just a way of organizing these numbers into sort of grid, a table. Okay, something important to note about these matrices are their dimensions. So when we talk about the dimensions of a matrix, we're talking about the numbers of rows and the numbers of columns that a matrix has. So here I've tried to color code what these dimensions look like. So here in this matrix in the top left, we have 2 rows marked with these red lines and 2 columns marked with these blue lines, right? 1 row, here's 1 row, and here's the second row, here's 1 column, here's the second column, right? So we say the dimensions are 2, 2. Similarly here in the top right, we have 2 rows and we have 3 columns. 1, 2, 3. So we say the dimensions are 2, 3. Here we have 2 rows and 1 column. So we say the dimensions are 2, 1. And here we have 3 rows and 3 columns. Okay, so that's what a matrix is. Something important to note is when a matrix also has one of the dimensions being 1, so it kind of just looks like this, or it could also look horizontally with 1 dimension. We can also call it a vector sometimes. When you get into math and deeper into math and linear algebra, there is a difference between those things, but for now I might call a 1D matrix a vector where one of the dimensions is 1. So don't get confused, but they're the same thing in this context right now. Okay, so another important thing is indexing our matrices, okay? So indexing a matrix is describing the position of any one of these elements in a matrix using the row and column that it's in, okay? So if I wanted to index this -1 here, this -1 here, I would say, well, it is in the second row, right? It is in this second row, and it is in this second column. So I'm going to use some coding syntax here. We say it's part of matrix A because this is A equals this. So it's matrix A. It's in the second row and second column. Notice these square brackets here are for indexing. This is not a matrix. Square brackets we use for matrices, but in Python and coding, we also use them for indexing. So this would be 2, 2. If I wanted to grab this 2, I would say this is in the first row and the third column. First row and the third column. Okay. And that's what indexing is. So we will get back to that later, but it's important to know what it is for now. Also, sometimes in Python, they will do something called zero indexing. So instead of calling this first row the first row, they will call it the 0th row. So instead, this would be 0, and then this would be 1. And then similarly, this would be the 0th column, this would be the first column, this would be the second column. So instead of 2, 2, it could be alternatively called, depending on what indexing we're using, which is always important to establish. Python uses 0 indexing, so that's why I'm mentioning it. We could call this 1, 1, right? Because instead of starting at the first, we're starting at the 0th one. It's in the first row in the first column. And similarly, we could call this 0, 2. Okay. So important to establish what indexing we're using. The one on the left is 1 indexing, I'll write that in. This is 1 indexing, and this is 0 indexing. Okay, so that's how we index our matrices. That's how we find what number they're in. So this is the -1 equals this, and this is the 2 equals this one, right? The 2 equals 1, 3, or 0, 2 if you're using 0 indexing, and the -1 is this one. Okay, now we have enough background to tackle matrix multiplication. Matrix multiplication is usually just shown as two matrices next to each other, and this is how we're going to tackle it. Okay, so our output will also be a matrix. And by the way, matrix multiplication is an operation defined by mathematicians, so even though it's called matrix multiplication, it doesn't look super similar to the regular multiplication between two numbers. So it's an operation defined by mathematicians, so don't get too confused asking the question, why is it this way? It's because mathematicians created this operation for the useful properties that it has. Anyway, this is how they defined it. So in our matrix, the matrix at position 1, 1, the first row, first column, we're going to use the first row of the first matrix and the first column of the second matrix, okay? And what we're going to do is we're going to multiply corresponding numbers in the row and column with each other, and then we're going to sum them up together. So in this case, this first one would be 1 times 2, right? 1 times 2. 1 times 2 plus 0 times 0 plus 0. So this would be 1 times 2 is 2 plus 0 is still 2, so this would be 2. Okay, and then we're going to go for the next one. This is the first row and the second column, so we will use the first row of this first matrix and the second column of this second matrix. So we're using this one now. We have 1 times 1 plus 0 times 2, right? 1 times 1 is 1. 0 times 2 is 0. If we add them together, 1 plus 0 is 1. So this is going to be 1. And then similarly, this next spot will be the second row, first column, second row, first column, right? 1 times 2 is 2. 1 times 0 is 0. So this should all be 2 if we add them together. 2 plus 0 is 2. And then this is the second row, second column, second row, second column. 1 times 1 is 1. 1 times 2 is 2. Add them together and you get 3. Okay, so that's how we define matrix multiplication. Let me do one more example here. Notice these had the same dimensions of 2 rows by 2 columns, 2 rows by 2 columns, but that doesn't necessarily have to be the case. Here we have 2, 3 by 3, 1. Okay. So first row, first column. First row, first column. 1 times 2 is 2, 2 times 0 is 0, 3 times 1 is 3, 2 plus 3 is 5, so this will be 5. Oh, blue, whatever. Then we're going to take, notice there is no second column here. There is no second column, so if we wanted to find a second column, we can't do that because there's no second column. So we can do second row, first column. Second row, first column, and that gives us -2. This is second row, first column, -2. And then that's it. So something important to note about matrix multiplication is that we're multiplying the rows of the first matrix by the columns of the second matrix. So the number of elements in any row on the first matrix must be equal to the number of elements in any given row on the second matrix, because if I constructed a matrix with like this times another one, let's just say by itself, then when I want to do the first row by the first column for the first position, a first row by the first column, you'll notice that, okay, the 1 matches up with the 1, the 2 matches up with what? There's nothing down here. So that doesn't work. You'll notice the number of elements in the rows of the first matrix must be equal to the number of the elements in a column in a second matrix. That's equal to saying the number of columns in the first matrix must be equal to the number of rows. Okay? Right? Because the number of columns is going to be the number of elements in a row, and the number of rows is going to be equal to the number of elements of a column. So the number of columns in the first matrix must be equal to the number of rows in the second matrix. Okay, the number of columns, because this is rows comma columns, right, in the dimensions, must be equal to the number of rows. So we've found something with matrix multiplication, and that is the inner dimensions, because if we sort of view these as sort of one thing, the inner dimensions of these must be equal. 3 and 3 must be equal, okay? What are the dimensions of this outer matrix, by the way? It's 2, 1. That's interesting. It almost looks like those are the outer dimensions. The outer dimensions, right? And that's not a coincidence. It came from the way that we did this. We said it's going to use the first row and the first column. So the indexing is going to be from this rows and these columns. But so the two rules about matrix multiplication that you should remember is that the inner dimensions of the two matrices that you're multiplying should be equal, and the resulting matrix will have the dimensions of the outer dimensions of the two matrices. So quick recap on how we do this. We're going to take in our final matrix, the first row, first column index. We're going to take the first row of the first matrix, first column of the second matrix, multiply the corresponding parts, 1 times 2, 2 times 0, 3 times 1, add them all up, and then we're going to put that value in here. And then we're going to say, okay, second row, first column, right? And then we're going to take second row, first column, multiply corresponding parts, add them all together. That's matrix multiplication. Okay, now that we've done all that, and I know it can be a lot to take in, it's quite an involving operation, but now that we've do that, I'm hoping that we can represent the forward pass of a single layer perceptron, an SLP, with matrix multiplication. Okay. So you'll recall that we generate the output of a single layer perceptron by taking the weighted sum of the inputs, x1, x2, xn, with their corresponding weights, weight 1, weight 2, weight n, so on and so forth. We add them all together, we add a bias term, and we pass that z through an activation function, and that's our output. Okay? So, the first thing I'm going to do to try to put these things, well, first let's assume, to make it simpler, that I have a single layer perceptron with 3 input neurons, okay? So I have inputs x1, x2, and x3. x2 and x3, okay? 3 input neurons, 3 inputs. The first thing I want to do is I want to organize those inputs into a matrix with dimensions 1 row and 3 columns. 1, 3. Okay? And then correspondingly, I will organize the weights. If I have 3 inputs, I should have 3 weights for a single layer perceptron. Then I will organize my 3 weights into a matrix with dimensions 3 rows and 1 column. Okay, so here's all my weights. 3, 1. And now I will perform matrix multiplication between them, and this should give me, okay, well, we know, okay, first of all, the inner dimensions match, so we know we can do matrix multiplication, and our output matrix will have dimensions of the outer one, so it will have dimensions 1, 1. Okay, so that's what we know. 1, 1. So it will only be one thing, because there's one row and one column, that's it. There's only going to be one value. And let's see what that value is. So we're going to take, let's see, this 1, 1. We're going to take this and this, and we're going to multiply the corresponding parts. x1 times weight 1 plus x2 times weight 2. I think you can see where this is going now. Weight 2 plus x3 times weight 3. Okay? x3 times weight 3. And this is only one value. Notice there's no spaces between this. In these matrices there are spaces, it's not addition signs. So all of this is one value. x1 weight 1 plus x2 weight 2 plus x3 weight 3. That's all one value. Has dimensions 1, 1. And that corresponds to our single layer perceptron only having one output neuron. That there is one output. But that's not it. This is all of this right here is only this much, right? So we still need to add the bias term. So we're just going to plus, and if we plus the bias, okay. And then we're gonna pass this all, and this equals z. And we're going to pass this all through, say, a sigmoid activation function. And then this is our output. Y hat. Okay. Now I'm going to call, so that's how we do it with matrix multiplication. I'm going to call this one capital X, because we use capital letters to denote matrices most of the time. So capital X for the input matrix, capital W for the weight matrix. And so we can streamline all of this as being y hat equals, well, first of all, z is equal to what? This was just x times w, so z is now equal to x times w plus b. And then we're going to pass all that through a sigmoid function. So y hat equals sigmoid of x times w plus b. Okay, and that's it. That's it. Okay, we did this for 3 inputs, but more generally, if you wanted any n number of inputs, any n inputs, then you would just need your input matrix to have dimensions 1, n, right? So instead of 1, 3, you would have just organizing it with with n inputs horizontally, and then your weight matrix in order, so you would have 1, n. If you wanted to do the matrix multiplication, you would need the inner ones to match, right? So your weight matrix would have to have the first dimension n rows, and then it would have to have 1 column because we want it to have 1 output because we're doing a single layer perceptron. This way, when we perform the matrix multiplication, which we can do because the inner dimensions are matching, then we will have a resulting matrix xw, x times w, with dimensions 1, 1, which is what we want. So that's how you do it. That is how you represent matrix forward pass of a single layer perceptron with matrix multiplication. And this will be useful for us when we go to actually code, because it will help us just organize all our things into one object, and instead of having to define a bunch of different weights, we can define one weight matrix, one input matrix. It will just make our whole life a lot easier. So that's it for today. I'll see you next time.